moving, it's capturing the disk. That's going. Start the audio. Missing anything else? Hi everyone, we'll be starting in a minute. We just wanted to make you all aware, if you haven't already, please grab a slice of pizza. Or a drink for it? Sorry. Drinks in the back. Drinks are in the back. We're happy that we've only started about a minute.
Beer and soda in the rear fridge? Yeah. Oh, sorry. Oh, downstairs for the doorbell.
So I'm going to leave this unmuted now. We're going to do a little intro roll and then the intro slides. After the intro slides, I've got to switch the projector from my laptop to this machine. That might take a moment to sort that out. Is that right? Yes. Yes, I'll do that. Xbox. Okay, we're starting here. Yeah, I should be calling you now. From the live stream?
Yeah.
Oh, you know what it is? That hum is coming from my laptop. So I don't know what the latency on the... Is that better? Yeah, I don't know what the latency is. It's probably like a minute or something. Can you let me know when it catches up? Oh, it says you're not available. Let's try again. It said it's calling you. You want to try calling me? Yep. There we go. Cool. It's also my video and audio. You should be able to bring up the slides. Yes. Yes. That looks good. I haven't run the projector yet because it's not hooked up to this machine, but we'll put it across and then we'll get going. But I think, so we're going to kick off in a second. I'm just going to mute the speakers on this one now. That's recording. It's not my phone or something.
Probably the door again.
Should be asking.
Yeah. Maybe next time we use that. Yeah, I'll try to jump in.
Well, let's wait. Did he go downstairs? So
He may have, yeah. Okay, why don't we get started? Good. 1 second. Oh, no, don't do that. Don't do that. No, not next week. Next time. Okay, good evening, everyone. My name is Neil Pandya. I would call to the 8th monthly Cyberspectrum Meetup. This event series serves as a forum for the exchange of knowledge and ideas related to software-defined radio, and generally aims to get people excited about the applications that can be realized with SDR technology. Engineers, students, hobbyists, enthusiasts, and people of all experience levels are welcome, no matter what your software or hardware background. People from the community will have to present their work, projects, and ideas to the group. The event tonight is being sponsored by Edis Research and is being hosted by Noisebridge, a nonprofit hackerspace for technical creative projects. Our first speaker will be Matt Riley, who is speaking remotely from the East Coast, live, where it's 3 hours ahead of us, so thanks to him for staying up late tonight. He'll be giving a called Soda Radio, a general purpose transceiver. Matt is a self-confessed radio geek. He's been a ham since 1979, now Kilo Bravo Charlie, and has spent way more time building radios than actually operating them. Most of his operating time now is during the annual ARRL 10 gigahertz and up contest. Matt has worked in the computer industry for the last 30 years, mostly in high performance and parallel computing systems. Matt lives with his wife, Ann, and his son managed to lure him out of the basement often enough to keep him healthy. Our second speaker will be Josh Meyer. He'll give a talk titled Decoding Radio Data System, RDS, from FM broadcast stations. Decoding Radio Data System from FM broadcast depth SDR project. Josh will walk through his implementation in IPython, starting with a sample capture and ending with decoding some of the RDS protocol frames. Josh lives in the radio noise mess that is San Francisco and is currently working on data acquisition and signal processing feedback project. He's also in the beginning stages of a few radio capture and direction finding projects. The presentations will be recorded and posted online, as well as streamed live on YouTube. The previous events have all been posted in full HD audio already. We have set up an IRC channel called #Cyberspectrum on Freenode as a way for remote people watching the live stream to contact the group here at Noisebridge with comments, questions, or any audio-visual problems. Future presentations will alternate every month between Edis Research in Santa Clara and here in San Francisco. The next meetup will tentatively be held on Wednesday, July 29 at the Edis Research office in Santa Clara. A list of speakers and presentations will be posted. If you have any ideas about for future talks and presentations, let us know. We would like to thank all of our speakers tonight for their efforts and enthusiasm, and we would especially like to thank Noisebridge for providing this space and hosting the meetup here tonight. We would ask that you leave a small donation in the donation bucket by the entrance to help support them. Free pizza, beer, and soda are available courtesy of Edis Research, so please help yourself at any time. Here, beer and soda is. So without any further delay, let's get started. We'll make a few additional announcements, and then we'll introduce our first speaker. Thank you.
Yeah, I didn't get you on the live stream, but I recorded you on there. Thanks everyone for coming. I'll just do the normal quick intro spiel here. Any reports from the internet as to how things are sounding and looking? A little bit of fun, but better than it was. All right. Oh, it's coming out right here. So we have already quite a few people watching online, which is great, people in the IRC channel. As Neil mentioned, we have our remote presenter actually right here. Matt, can you hear me? Yep. All right, great. So we'll switch over to this laptop in a second. I'll just go through these usual slides for those out there, as well as here if you want some more information. So this is our 8th Cyberspectrum, which is very exciting. If you want to jump on IRC, we've got plenty of people there. It's #Cyberspectrum on Freenode, and this is also remote. People want to ask questions of the presenter here. If you see them asking questions, just feel free to shout it out and relay it. That can happen quite often. Neil already mentioned, but thanks again to Edis Research for the pizza and the drinks, as well as Noisebridge for hosting us yet again in this really cool space. If you have something you'd like to talk about at a future meetup, or you know somebody that might be interested in this, please spread the word so people can find out about our little meetup and show all the cool things that you can do with software-defined radio. After the... What about the mic? We'll speak into the microphone. Or the grab mic, or the internet mic.
Well, both.
Both? All right, I'll try both. So remember that after the events, if you go to the meetup page, there's a link there, and it will list all of the meetups that have occurred till this point, and in those pages it'll contain a link to the video. This live stream gets archived automatically, and then later on we put the HD version up. And in addition, it'll also contain hopefully the the slides and presentations that the presenters will post. So usually we aim for the last Wednesday of each month, but we'll be back down in the South Bay, so keep an eye on Twitter and on the Meetup page. I'd like to make a call out, and anybody's free to do a little show and tell, or if they have any messages radio related, feel free to come up and talk about it. But I'd like to do a plug for the conference 2015. It's in August, and 24 to 28 in Washington DC. It's been growing in size really, really well over the last couple of years. It's a great way to get what's going on in the community, how GNU Radio itself is developing, and all sorts of out-of-tree modules and experiments that people use it for. There are going to be presentations, tutorials, hands-on events, and also a hackfest and booths and all sorts of interesting people coming together there of all areas of the spectrum. You're supposed to laugh. And there's also registration for students. Oh, well, I saw Matt grinning there. Thanks, Matt. I saw that. That was great. So, yeah, keep an eye out for that. And so, first up, Matt Riley, also known as the creator of that's box. I'm showing them your Shack in a Box photograph. So maybe you'll tell us what's actually in that Shack in a Box. And then second, we have Josh Meyer. And there's his Twitter handle if you want to follow the cool things he's up to in the SDR world on Twitter. So without further ado, if you just give me hopefully a minute, I will switch laptops and then Matt. So give me 1 second. Was that all good? Talking to the mic.
software that was pre-canned. I wasn't going to learn much about that. And on Windows, and life is too short. So SOTA was built originally for the USRP. And you see the title slide there. It was an experiment in software-defined radio. The presentation will have a little bit of SDR fundamentals. So those of you who are new to SDR, there will be a little tutorial partway through. Those of you who are experienced in SDR, please feel free to steal the images and the animations and for your own presentations. So why did I do SOTA? To learn the basics of practical SDR design. I found that for me, the easiest way to learn something is to actually build something, and build something that's serious, more than just a toy. We all learned something from writing our first Hello World program, and that's a big breakthrough for most of us. Whenever that happened for you, I'm sure it was a big breakthrough. But you learn a whole lot more from your first compiler. And my object was to jump into something where I'd have to do the whole, solve the whole problem end to end. And it needed to be a practical SDR, one that was a field. It was a lab. It was originally a transverter IF, that is the last strip in a microwave radio that goes from microwave transfer through a mixer, an intermediate amp, down to what had been a fancy commercial VHF radio. So what I wanted to build was an SDR that was equal to my fancy commercial VHF radio, which was, by the way, for those of you who are part number junkies, a Yaesu FT817. And so it ended up being an all-mode VHF, UHF, and lately a medium frequency and all-frequency radio with the addition of the UBX module. Great job, Edis Radio. If this sounds like a plug for Edis Radio, well, fine. You're eating a pizza. Okay, so the SOTA radio system. By the way, Val, is this coming across okay? Does this look okay? I'll pause.
Is it all good?
Yes.
So we can hear you.
Okay, good.
There we go.
Thank you. So here's a block diagram at the very top level. We have the GUI on one side and separate the GUI from the SDR controller and all the signal processing and all the audio stuff and everything else. Partly because I had an ambition one day to be able to connect up to the radio from upstairs from a more comfy chair than the one down in my lab. In the end, I bought a much more comfy chair for down in the lab. The other reason for separating out the GUI is there's just so much time crap in a GUI, but it's not nearly as critical as the real-time stuff in the radio itself. Then in the middle you see the server and the controller that talks to the USRP through libuhd. I love GNU Radio. GNU Radio is really cool. It's democratized access to SDR. Unfortunately, it does way too much for me, and I really wanted to learn what it was like to write a resampler, for instance. So libuhd was the answer. It also provides you an awful lot of control over the box, and fairly transparent control. Down at the bottom is the Linux audio drivers and libs, and let me add my voice to the screaming voices of the thousands of people that have ever written a Linux audio application. Wow. 20 years of Linux, and this is where we are. And then on the right, via an Ethernet connection, and laterally via a USB connection to a USRP. SOTA runs on an N200. It also runs on a B210. I'm pretty sure it's fine on a B200. And my suspicion is it would run on any of the net or bus connected radios. Unmute the audio and yell at me if this is getting tedious, but I figure a few signal junkies there. At the top you see, this was the block diagram back when I was using the WBX module. We go from the antenna through a pair of mixers driven by a first LO, and then we do the A to B conversion in I and Q. So we and we go through another down conversion at the second LO. Now, a lot of EDIS users use the USRPs as direct conversion radios, so the final output to the computer is baseband. They also use the tuning as a unit, as an entire unit, so that the front end and digital second local oscillator are tuned together so that they can get down to baseband. SOTA doesn't do that, partly because of a desire to get a convenient window that was far in the periodogram or the waterfall diagrams. I wanted to avoid having that white band that you always get for component first mixer. So we tune the first local oscillator a couple hundred kilohertz to several megahertz away, depending on the front end. And then we tune the second local oscillator still a couple hundred kilohertz away from the signal of interest. And we eventually beat it down inside the computer down to baseband. So I'm not using this as a direct conversion radio. You see the resamplers inside the FPGA, and then we get INQ that go off to the host computer. Exact opposite on the transmit side, except on the transmit side, I believe SOTA now does baseband. If you squint close enough, it's just baseband, direct conversion. So let's talk about INQ. INQ is probably the only really new thing with software-defined radios that you don't see in an analog radio. That is, in analog radios, if you want to pick out a sideband or something like that, we use filters. With an SDR, we have the advantage. Whoops. Oh, come on. There we go. I spent so much time on that animation, I wanted to see it. So the I and the Q channels describe a circle in IQ space. That is, if I get a steady carrier coming in, I get coming out of the I and Q. And that's a useful illustration to keep in your mind because almost all of the demods have something to do with that circle. So I and Q tricks. One of the neat things about I and Q is demodulation gets really simple. For upper and lower sideband and CW, we just take I and Q, shift the Q channel one either 90 degrees forward or 90 degrees backward and add it to the I channel, and we pick out the sideband we want. As somebody who's built an analog radio or two, sideband operation in a real analog radio is an interesting and gymnastic trick. It either relies on narrowband, expensive crystals, or it relies on extremely crazy arrangements of phase shift networks that very few people are competent, and I'm not sure I was competent to build, though I did build one or two of those. For AM, you just take the square of the I and Q channel, and you can take the square root if you want, and get a little less distortion. For phase modulation, like FM and PSK and phase modulation, frequency modulation, or phase modulation, all we have to do is an arctan. And arctan is a reasonably zippy operation. Those of you who have ESP textbooks, they talk about all these fancy I plus Q over I squared over 2 plus Q squared over 2 or whatever ratiometric means of escaping the task of tangent. But if you're running on a modern x86, do the arctan as fast as the divide, and you get a much better signal out of it. It's much more forgiving than all of the high-speed tricks that you saw in the textbooks from 10 years ago. And the rest of this is I and Q streams. You get twice the number of samples. You get the sample from I and the sample from Q. So you get to watch frequencies minus F the Nyquist frequency to plus F the Nyquist frequency. Take a look at what the CW or USB or LSB demodulator looks like in SOTA. It's a chunk of code. Compared to the number of analog parts for my last analog SSB radio, this was a dime. And in fact, all the stuff is in just a few lines. The Hilbert transforms to get a 90-degree phase shift in one of the channels, the Q channel. And then the middle thing is just decide to add or subtract the Q channel. And then finally, we add or subtract the Q channel to get the audio out. What a deal. So those are the two key lines in that code. Now let's look at an AM signal. As the signal gets bigger, the IQ circle gets bigger. As the signal gets smaller, the IQ circle gets smaller. So the object of an AM modulator is just to measure the radius of the circle we're describing. And I love this animation for hours. And if they're serving beer there, you could probably watch this for hours too. So that's an and let's look at what...
Matt, sorry to interrupt you, just so you know, everyone is giggling and really enjoying the comments, although I've muted it, so...
Thank you.
Good feedback.
I'll still keep my day job. So here's the AM demodulator. And again, it's about, 12, 13 lines of code with some comments. I remember somebody telling me once, in a survey of C++ and C code, they determined that the comment was the most difficult construct, almost never used. But this is the AM demodulator. Again, one call to the absolute value function, which is square root of I squared plus Q squared. Compare this to your typical AM demodulator in an analog radio is essentially a rectifier and a low pass filter. So this is a little more complicated because I had to do a square root, but still it's one more. And compare that to most other programming tasks that you have to do to get an interesting feature. I decided I wanted to demodulate an AM signal one afternoon, and so I wrote demodulate. Now, of course, we also pass it through an audio filter, and Sonar Radio, as you can tell, is written in C++, and there are there are a bunch of classes that help me to build filters that are audio filters or IF filters, Hilbert transforms, various other repetitive things. And I tried to encapsulate it in the best software engineering practice, at least the best software engineering practice that's basement lab. And here's an FM signal, one of my favorites. Now in an FM signal, the frequency is changing, and the manifestation in the IQ plane is the dot spins around the circle a little bit faster when the frequency goes up, and then it down as the frequency drops. So we see the frequency drop, and the dot slows down. So to demodulate an FM signal, what I want to do is measure the angular displacement of the dot as it spins around the circle from one sample to the next. So this is what the code looks like. This is the code. I take yard, which is arctan2. By the way, those of you who are math geeks, arctan2 rocks. It gets away from some of the divide by zero problems and the quadrant ambiguity. So you use ACAN2 to tell you exactly which of the four quadrants you're in, as well as what the angle magnitude is. And then we take that phase, that's the position of the dot in the current sample, and subtract the position of the dot in the last sample. Now, because the sample of the space runs from minus pi to plus pi, you have to do a little bit of correction, and that's the ugly code you see afterwards saying, if the difference phase is less than minus m pi, correct it. If it's bigger than m pi, correct it. And that takes care of the dot running clockwise or counterclockwise. And then finally, at the bottom, we do an audio filter just because it's nice. So here's a block diagram of the way SOTA is split up. I broke it up into a number of modules. Each one either handled some piece of the USR or some audio or the. Now, for those of you who are libuhd programmers or are about to become libuhd programmers, one of the things to remember is libuhd cautions that if you're going to do control come from the same thread, only functions you want to do in separate threads from the control thread, functions that manipulate streams. So, and even there are some caveats. Now, the code base changes, but the one durable lesson I've learned, the control flow for the USRP is not necessarily re-entrant. A lot of very good sound engineering reasons that they did it that way. And it's not that big a deal. So you concentrate all the things like setting frequencies, choosing antenna ports, setting gains, turning on and off audio, and things like that in the USRP object. Management of the transmit streams are in USRP TX, and receive stream, no surprise, in USRP RX. I split the audio parts out from the parts that talk to the USRP, partly because I have an ambition of having this run on multiple platforms, and also is really the audio library of choice for me anyway under Linux. I looked at Jack, and I looked at Pulse Audio, and I looked at a bunch of other things. Pulse Audio made my ears bleed. Jack, I couldn't make it work for Jack. So I ended up with Pulse. On the Mac, I experimented with Pulse Audio. I've since on my Mac, when I die, I want to be buried with the Mac. But when I die, I don't want to write real-time code for my Mac. So let's see, the other blocks in TX is a unit that translates text streams coming from the user into dits and dashes, and then creates a nice keyed envelope that has nice rising edges and falling edges, so we don't have a whole lot of key clicking, and sends them over to the USRP transmit stream. These lines that connect all the boxes are buses, and they're buses implemented with shared memory mailboxes. All the C++ coders are geeking out now. It's a templated class where you give it the type of mail messages that it's going to carry, and it manages queues for subscribers. One of these units subscribes to the command bus in blue. Some of the units subscribe to the audio bus, and some subscribe to the RX baseband stream. You'll notice that there's a baseband stream going to the user interface from the receiver. That's because we do an FF to either a waterfall or a periodogram in the GUI. And finally, in the lower left corner is an interface to my GPS. I use it as I like it, and it's sometimes used as a time source, but that's not nearly as important to me as the 10 megahertz source. What else can I say about that block diagram? Not on one slide. All right, so here's a block diagram again of the receive chain. Once we get inside the computer, we go RX, where we down convert to the final baseband, then we resample down to the audio rate, the demodulation. The exception is for wideband FM, we don't want to resample down to the audio rate before we do the wideband FM demodulation because the wideband FM channel is pretty wide. The mirror image, where we go from the audio at 48 kilosamples up to 625 kilosamples. Now why 625? That's kind of the lowest sample rate where the N200 is still comfortable. Look at all those filters. We'll go through this quickly. All of them are implemented in frequency domain. Stuff you learned in your signal processing class, that's a couple hours back. You're much better off doing all those filters in the frequency domain if you've got a general purpose processor, because it is wicked fast. If your filter is longer than about 20 or so taps, you're better off using FFTW or the Intel FFT implementation and do it in the frequency domain. Yeah, I said it beats FIR filters with more than 40 taps. Frankly, it beats FIR filters with more than 20 taps unless you are a numerics wizard. This is a picture of the filters. They're all 512 taps. that gives you some pretty steep skirts. You'll notice that on the CW side, the 100 and 500 kilohertz filters, those skirts are pretty steep at the upper edge. Steep enough that I think you'd probably go nuts if you had to listen to it for more than a weekend. And here's the GUI was to what I needed to run my 10 gigahertz transverter in the 10 gigahertz contest. Anything else is kind of, there's a waterfall chart at the top, and it can turn into a periodogram, and then the controls at the bottom. And we'll see the controls more in a minute. So let's do a demo. Oh, I implemented the GUI with Wix widgets. It's kind of portable. Connects to the SOTA server by a Unix domain socket rather than going out over the net. It's not as insecure as it could be. So let's do the demo. Balint, I think now on the other widget. Or do I call you?
I'm calling that way. Maybe it's better if you call. That worked last time.
There we go. Oh. And it should be happening. So while we're waiting, okay. Now, this 2-meter beacon, and I think might be a good time to mute me.
I think you need to share the screen still. It's not coming through here.
Oh, okay. Where'd it go? There it is. You see it now?
Yep.
Okay. So this is SOTA radio listening to a beacon. And
I don't suppose you can make it a little bit bigger on your screen?
that's a guess.
Okay.
And Val, what if you wave your hand in front of the screen if you know?
We can hear it, but it would be good to make it just a little bit louder.
Okay, let's try that.
Can everyone hear that? Yep. Yep, we're getting notes from the audience.
Okay, that's a beacon from WA1ZMS in FM07 FM. And SOTA radio tells me right here, 3 kilometers away. This is through the crappy little disco antenna on my, because I live in a neighborhood that has antennas. By the way, this stuff at the top, you can see something that's blowing a raspberry at the waterfall diagram. If we get attention on a periodogram every now and then, actually we won't, it'll go by too fast. That is a Bell 212 modem. It's somebody reporting their position every couple of seconds, like I cared. So we're looking at the waterfall diagram. We can zoom in, and the 2 very faint red lines are the bounds of the filter, and I can crank the filter down, move it around a little bit. But more interestingly, I go down a few kilohertz. Here's my friend. I'm sorry, that first loud beacon was actually the W3APL beacon that's 10 kilometers away. This beacon is 300 kilometers away, and it's very weak. And I'll take you on a quick tour, just because I think it's the coolest thing since I got this UBX module. That's at 2 meters. So let's go down to 6 meters. this is the W3APL over at the Applied Physics Lab. Let's go down to 10 meters. This is the W3APL beacon over at the Applied Physics Lab. Let's go to this is WWV in Fort Collins, Colorado at 15 megahertz. Now this again is the UBX. Now let's go down to, this is WBAL from Baltimore, AM 1300. I think that's BAL. And it sounds every bit as crappy as a broadcast AM signal. But again, remembering this is on a dipole in my attic in a house that's full of fluorescent lights. Now for one more stupid pet trick, watch this. The signal at 260 kilohertz. And this is a signal from a signal generator across the room at 260.1 kilohertz. Put it on CW. And there it is. And I know it's on the thing across the room because watch the waterfall diagram, and as I twist the knob, it wiggles back and forth. I hope it wiggles back and forth. Back and forth. And one other silly pet trick. This is at 5.8 gigahertz, again with the UBX module, and a signal from my sweeper. Let's see if I can get the sweeper to come across. Oh. Yeah, of course, the reason I showed the train wreck on the demo. Ah, there we go. Let's try that. Somewhere in there is a sweeper, and it just stopped making enough noise for you to hear it. But in a few seconds, we tuned the radio from practically DC to just a little bit shy of daylight. There we go. So that crappy signal that you see in the waterfall diagram is actually a sweeper that's kind of wiggling around. Let's see if we can. And that is the characteristic sound of the sweeper because they are incredibly swirly. But that's at 5.869 gigahertz, all on one radio. One of the reasons why I'm just tremendously pleased with the UBX module. You never know when you might want to do a microwave contact and then listen to somebody's key fob responder. Okay, let's see. Did anybody have requests for any part of the demo? Is there something they'd like to see?
Any requests? Anything from the internet? Quite caught up yet because it's a delayed stream. You want to ask online if anybody's got any questions?
This, by the way, is China Radio International. And a little while ago, they were doing the Learn Chinese via shortwave radio. And there was a really peculiar shape to the modulation. It looked like an AM stereo signal, which I thought was pretty cool. The other thing periodogram has been used for, I've used it to characterize some of the noise in the building. I've also used it as a noise figure meter and as a sun noise meter. So I can crank the resolution down enough so that it's 1 dB. Unfortunately, I've never been able to build anything demanding of that. So, Val, if we could go back to the Mac to finish up the presentation.
Sure, I have a question for you actually.
Sure.
So with the feature set that you have at the moment, where do you see it going in the future? What sort of features do you want to see added to it?
So, some folks have connected SOTA radio like tracking system and the satellite ground station. They did a valiant effort, really nice work. They worked their butts off to actually make use of my code. I think I owe them a better socket into the code for remote tuning. That's one. I'm working on, the latest thing. Oh, yeah, you'll see in a minute. Some test equipment. I frequently end up using SOTA radio as a signal generator, and often enough I use it as a signal sniffer. That really wants something a little bit more broad, so the waterfall diagram isn't quite wide enough for a good signal. The rest of it is I'm listening to what people want. Oh, yeah, the stuff that was done recently. I added GPIO control for transmit and receive switches.
Could you share the screen again?
Sure. Did I do that? Is it there? So here's the big blue transmit button. So if we switch to a band where we actually
it's not actually showing.
Ah. Is it showing now?
No.
How's that?
No, do you want to try switching back to your video and then starting screen sharing again?
Yeah. So I'm still connected. So if I do that, now.
Yep.
Okay. So we're back on 2 meters now, and I'll move up to a place where I'm not going to offend anybody, except maybe the guy who's where he is every 30 seconds. And I'm going to turn off the sweep rack. There we go. That quiet. So that's the side tone. So it transmits to, and it listens to itself. I don't create an artificial side tone. That the tone that you heard was actually the receiver listening to the transmitter as it transmitted. So that was leakage inside the box. Outside the box, we still need a way to switch over the transmitter and external amplifiers and anything else that's out there. So for the N200, prototype TR switch out of an Arduino and a cheap bit of, there we go, an Arduino and one of these optically isolated relays that you can get from Alibaba for less than the price of the parts. So Lord knows what truck those parts fell. I'm glad they had bumpy roads wherever it was. So there's a TR switch that's coming out soon for the N200. It's an Arduino sketch with some code that uses the GPS serial port. For the B200 and B210, there will be a circuit that I'll post soon as I get it working reliably, that uses the J400 GPIO pins and a special FPGA image to control a TR switch. Both of those get me to the point where N200 and the B200 in any of the transverters that I've built. And that's been a fair amount of the work in the weeks. There's a mode for the B210. Let's do this. Here's my B210. transmit channels. The second transmit channel to create a heterodyne oscillator to get a 10 gigahertz signal out of the B210. With a fairly inexpensive 10 gigahertz radio with about $100 worth of additional parts. Any other questions?
We had one from the internet. Could we see the 50 megahertz band?
Sure. 6 meters. And you'll notice the RF way down. There's a fair amount of 50 megahertz noise in the house. You can see is probably from, well, this one is at 50 megahertz on the button, and that's probably from one of the many Ethernet devices around. But the band is actually fairly hot, or was on Sunday. I haven't been listening a whole lot. There's some other beacons here, but it's demo time, and if I lit up one of the other beacons, my hair would fall out or something like that. This is the W3APL beacon. And actually, let's zoom in on that and look at the periodogram. So it's 20 dB out of the noise, which isn't a surprise because I could probably throw a rock and hit the applied physics lab from my house. Probably not throw, but it's a few kilometers away. And you'll note that I can split the transmit and receive if for some reason that seems like a good idea. There's a control for output power and side tone volume and CW speed. And then down here, the buttons all automatically send the exchange that's needed in the 10 gigahertz contest, which is a very simple exchange that amounts to, ooh-wee, I hear you. And I am here in my 6-digit grid square. Are we ready to go back to the other side?
We are indeed.
Okay. So let's turn the audio off, and I will call you on the other one.
Great.
Let's see. So we do this. Good. Right. And finally, last little bit of the slide presentation, and there.
Are you calling me? Matt, are you calling me?
Yes, I am.
Okay.
Oops. It looks like you aren't available. How many of you are there?
I'm calling.
Let's see. Let's try it again.
Giving you a buzz.
Ah, good. Is that you?
Is that ringing for you?
Not yet. Let's see. Oh, you calling on the link box? That's Matt.
Yeah, I thought I was.
Yep. And if that doesn't work, we will wrap it up with just plain old audio. There we go. Calling?
Yep.
And I just have a few more slides. And do you see the slides?
Yep.
Okay. So Soda Radio is on Source. Go to SourceForge, download. If you have problems, send me an email, and I'll see what I can do. You all already know how you can play. You talk to Ballant, and you write a check, and Matt Ennis picked everybody up. The M200's one entry point, the B200's the other one. And I'm going to plug a set of headphones in. There we go. And what I really wanted to get to is, there's a question on the US list, and the question is roughly, how do I know how much power is coming out of this whatever? And here's how you know. You spend $200 on eBay, or actually you spend $400 and you throw out the thing you buy with the first $200. Probably get 2 tries to get one that works. The best bet is this HP 432 active power meter. Don't buy it unless it comes with a thermistor mount. You have to get them all 3 together because it's the thermistor mount that's got all the magic in it. And those are the things that are missing most often. But for under $200, it's good from 10 dBm all the way down to practically minus 15, minus 20 dBm. The thermistor head that I list there, it's good from 10 megahertz to well above 10 gigahertz. I've had mine for 15, 20 years now. You also need a whole bag of SMA attenuators. It's worth buying a bunch. And since I'm sitting at my desk and looking at a bunch of parts on it, and you guys are in the noise bridge. Is that in the frame? I think it probably is. You don't need one of those. But I have one, and you're sitting in the noise bridge room. And the other thing is people building scalar network analyzers with the USRP. This is where I want to test the response of a device under test to an input and see how good the filter is. I'm doing this with the USRP because if you transmit 200 megahertz, inside the box, the receiver is going to keep the transmitter no matter what you do. And it's going to keep it not attenuated very much, maybe 20 dB, maybe 30. And 20 dB just isn't an interesting dynamic range for a network analyzer. You want something a little better than that. So one way to get spectacularly good dynamic range is to transmit 10 megahertz away from where you're listening and add the oscillator externally. And that looks like this. And there's the label of the diagram, and I've got the same thing in my hand. So if you're building a network analyzer, this is one way to do it. I have since decided it's not the best way. I expect a course in this. This is the way to do it as a classroom demo. Now, years ago, when I first got my USRP, I wrote a scalar network analyzer application. The bits have rotted, and in fact, I can't even find them anymore. But I did have this image left over of a 1296 megahertz filter Paul Wade W1GHZ had built. And at some point, I want to make it part of Soda Radio, but we'll see. And finally, this is it. This is a view from Block over toward Rhode Island. I think I did that right. Yeah, we're looking west, the sun is setting. That's the shack in the box with Soda Radio up on it and my 10 gigahertz transverter. And that's it. I'll unshare. And if there are any questions, I'm happy to take them.
Any other questions from the audience here or from the internet? Can you hear me, Matt?
Yes, I can.
Somebody asked, can I connect remotely to your setup that is just running the GUI from my laptop.
Oh Lord, no. That's like leaning on a lamppost. It's just a bad idea to open a socket up to the network. At some point, add SSH support. I'm not inclined to have anything hang out and listen on a TCP port. There's bad people out there.
Okay, fair enough. Well, with that, let's thank Matt for his presentation. You've done some really amazing work there. It's great to see it maturing to this point, and best of luck with it in the future.
Thank you very much, and thanks for the help from Edis, because and I needed a hint, and Edis has been very helpful in the discussion group, the mailing helpful as well. And it's always fun to watch the comments roll by. Well, enjoy the next presentation. I'll be watching from here.
All right, thanks again.
Good night.
All right, so we'll switch over to our next speaker.
Works this time. Okay, so earlier on I actually set up everything to get Linux on here working. I don't think it's working, is it?
Yeah.
Hello? Hey, there we go. So earlier on I did the ritual half hour of getting Linux to work with Projector, and then I had to disconnect, so we may be in for... That's going to be a hard act to follow, by the way. That was a really great presentation, and it did a lot of the things that I was interested in doing, specifically around doing SDR for S people. Or sorry, yeah, for software. I got into this years ago, sort of, and it was really hard back then to find out what was going on and what you needed to know in order to actually succeed at SDR, especially without an actual background. And a project like Soda Radio is fantastic for finding out all the things like, here's how you do AM in an IQ signal. Let's see if we can get this to work again. Oh, and for the record, early on in the noise bridge story, there was a conversation of why isn't there actually a noise bridge. That was the old noise bridge.
It's in the book.
Okay, so, okay, you're gonna have to forgive me, I have to set up a bit of context again. This one is an IPython notebook. If you're somebody who has IPython set up already and you have an RTL SDR dongle, you can actually follow along at home. So if you go to john.com/project, hit enter, there'll be SDR snippets on there. And then under there, there's going to be GNU Radio and IPython. And then in there, there's a thing. I'll write it down for you in a second. Okay.
I am also going to sign up for a train wreck. This is actually the code that we're talking about. I'm going to try and run this. So I've got standard RTS, excuse me, RTL SDR dongle here, which I'm going to plug in, and we're going to try and actually use. So this is IPython. If you haven't used it, it's actually pretty great. It lets you run interactive Python, which is excellent. Okay, cool. So we're just going to do a bunch of stupid stuff to get set up. Okay, cool. We're now set up here. Okay, hi, my name is Josh. I'm going to talk about the radio data system. This is how your car winds up getting the, here's the thing to go to if you want to follow along. This is how your car knows what song is playing. It's a really interesting and in-depth first project in software-defined radio. And it's actually the thing that got me interested in SDR again and got me off of my butt to actually get my setup going. There are several other implementations of this, all of which actually work far better than mine do. The first one is by Ona, who is, she just does amazing stuff in Perl, which is kind of mind-blowing to me. She makes pretty things in Perl. And her implementation, she spent a bunch of time reverse engineering the bus shelter messages in Helsinki, where she lives, how that all works. She also reverse engineered and cracked the encryption used, and I think encryption goes in quotation marks here, for traffic data over RDS, because that's another thing that goes out over the system of where there's accidents and so on and so forth. The other implementation that's worth looking at if you actually want to do RDS is this one by Dimitros, GRRDS, which there's a fork of it at Balance, moved over from Bitbucket. There's another one up on GitHub. There's probably several others, but they're kind of all the same thing. So what is RDS as a signal? It is BPSK, binary phase shift keying, at 1187.5 hertz, which we'll get into in a minute as to why that is. It sits on a 57 kilohertz audio subcarrier inside of your regular FM audio, just on a standard station. And it's encoded in 26-bit blocks and 104-bit packets. So it's kind of small little chunks of data, and they get even smaller once we get into them, sent at this really slow bit rate. But it's out there, and it's a great signal to get into, because you go through so many steps, which we'll go through. If you Google around, or if you look at what Ona has documented, she links to this PDF of RBDS, which is the American version of RDS, because the Europeans designed it, and therefore we need to take it, rename it, and change a few things to make it ours. It includes some really helpful schematics. The first is the encoder phase, and then the second one here is the decoder phase. And you can have a look at this. It's all these fairly standard things. You got the 57 kilohertz signal lock used for both the 19 kilohertz pilot, yada yada. And if all of those things make sense to you, I'm sorry, you might be a little bit bored. This presentation is meant for people who don't quite understand how radio works. It's mostly SDR for S people. I'm very self-taught, and it turns out that most of us who are self-taught are not so good at studying textbooks as we are finding things and tearing them apart and understanding them that way. And this is an exchange on Twitter recently. Also, don't follow me unless you want to. I tweet a lot of random crap. So anyway, this is a conversation-ish. I posted this statement, and then the guy who replied here is, if you do QRP stuff, you might have come across QRP Popcorn. It's VE7 BPO. He does lots of amazing schematics, lots of amazing designs. And it turns out that, yeah, he's learned things this way too. You find something, you take it apart, you try to understand every last little detail in it, and then make it your own. I also make these slides for people reading them later, so this is all the notations I'm going to use. I'm going to skip that since you're all in the room. So this is the slide that is intimidating. These are all the steps that we need to go through to actually implement an RDS receiver. We need to pull in our samples. We need to demodulate the FM signal, i.e. pull out the radio station. We need to pull out the 57 kilohertz subcarrier from that. Then we need to PSK demodulate that. Then we have to differentially decode the bit stream. Then we have to find our packets, because we just got this string of ones and zeros. And then we need to actually parse and extract the packets. Capturing the samples is pretty easy. Okay, is this the actual live one? Sorry, I cheated. I'm going to go ahead and uncheat, actually. Okay, so that's the one this is live. So just a minute ago, while I was getting started, I went ahead and actually did some capture. So this is IPython. Is everybody here kind of familiar with IPython? It lets you type in Python, execute it, and get graphs and things inline. It's really handy. So I am pulling data from 1045 KFOG here in San Francisco. Okay, so this is what's on there now. Okay, people recognize that song roughly. So it's capturing right now. We'll go back to the presentation. It's in the background capturing. It's going to pull up something like this. This is a periodogram or a PSD of the captured signal. This is what FM looks like. This is the actual FM audio signal. And then these two big sidebars there are our digital for HD radio subcarrier. Then this little spike here is the DC spike. Matt mentioned is you have an LO that's offset from an LO that's offset from so on and so forth to avoid. He goes to great pains to avoid that in his setup. With this crappy little $20 dongle, you don't get the choice. You're going to get it. So we're going to deal with that here in the way that we choose to capture our samples. It's funny, too, that he said that wide FM is very wide, because that was something that I called out in my slides as well. We also wind up choosing a sample rate kind of oddly. If we look over here, the sample rate, can people read this, or should I make it a lot bigger?
Bit bigger?
Bigger. I should make it a lot bigger. Okay. Oh, man. It's being a little bit wonky. So our sample rate here, FS, is 57 kilohertz times 20. And this is done because that 1187.5 bit rate is actually derived from the 19 kilohertz pilot, derived from the 57 kilohertz standard oscillator in FM. Just lots of trivia. Anyway, so we choose that. We also choose our number of samples very carefully here, just because LSDR dongle is picky about how many samples you request. So we do all that. Let's see. Uh-oh. That does not look right, does it? Okay, so let me run this again. Sometimes my sample fetching doesn't work quite right. And that didn't start happening until the other day when I upgraded things. Anyway, okay, so we pull in our signal. Then we're going to FM demodulate. This is what an FM audio signal looks like. Who here is familiar with FM in general? Sort of? Okay, cool. So inside of your FM radio, there is a lot of complicated stuff to pull out this audio. And then in this red section is the monaural audio. It's the monophonic, non-stereo audio. It's the simple stuff. Lives down here. Then there's this 19 kilohertz pilot that lets you figure out exactly where you are and track the signal properly. Then over here we've got our stereo, which one half of this is what you if I remember correctly, subtract from the left, and the other half is what you add to the right or something like that. It's kind of crazy. And then out here, this little like Totoro ears is the signal that we're after. Out here at 57 kilohertz, that's RDS. The reason there's two bumps is that we switch between two frequencies as we signal. To actually do this demodulation, let's see if this works better this way. There we go. There's lots of ways to demodulate FM. Most of them are awful. So the way that was actually kind of how we're going to do it. But if you look in the documentation that companies have put out with their chips and so on and so forth, there's lots of really complicated ways to do FM. Because what you're trying to do is track a frequency as it moves and then turn that into an amplitude. And these other two ways, by the way, are generally better. They deal with drift in your clock and so on and so forth better. But we don't need to do that. So what I'm going to talk about here is explaining a function that's basically 2 lines long in about 5 slides. The function in question here is demodulate quadrature CF, which is quadrature demodulation, i.e. FM and K. We need to start out explaining a couple of things. First off, this is what FM does. Your frequency at any instant in time is your carrier frequency plus some adjustment for the amplitude of the signal you've got in, frequency modulation. And there's a different frequency. You can look at it as so many hertz, or you can look at it as angular frequency, which is so many radians per second. And that goes back to the circle that Matt had. He actually set me up with diagrams that I couldn't have made. So that W here is actually an omega. Anyway, omega, which is the rate of that little dot spinning around the circle in radians per second. So that's step 1. We can kind of see that our input signal, which is this X thing, turns into angle, right? The change of angle over time. Now I'm going to do a quick complex math refresher. Complex numbers, A plus BI, or BJ if you're an engineer. I still don't know why, to my satisfaction. You can write it either as that AB coordinate thing, or you can think of it as an angle and a line along that angle. So there's 2 notations for this. One of them is algebraic A plus BJ thing. The other is the polar form R at angle theta. So there's a thing here as well, which is the conjugate operator, which is basically you just switch the sign on the imaginary part, which takes things that are above the x-axis and puts them below it, and vice versa. And if you think about that in the angular form, in the polar form, you take a positive angle and make it negative, or vice versa. So this is all leading up to this last step here. Whenever you multiply 2 things together, 2 complex numbers together, you can do FOIL, first, outer, inner, last, or you can do it in polar form, where instead of having all of these crazy things to keep track of, you just multiply the 2 magnitudes, how long they are, and then you add the 2 angles. That's it. Like, the angles just add up. It's kind of handy, especially when we're working in FM, where our signal is encoded as how fast the angle is changing. Does that make sense to people? You're kind of my control group because this is a video, so I need feedback because this is forever. So, is this making sense to people? Kind of? Okay, cool. So, if we want to find out the difference in angle between 2 complex numbers, we can take the conjugate of one, then multiply them, and then get the angle of the result. Right? Because we take the conjugate that makes it negative, then we multiply them, and the 2 angles add up, except now one of them is negative, so we get a difference. This one is a slide that drives me a little bit crazy because I'm a math person. I have a math degree. Nobody here really cares. specifically, there's some stuff about instantaneous rates of change. The important thing here is our signal is encoded in this omega, right? And we want to at any point in time because that tells us what our amplitude is at any point in time. We can do that by taking the angle of our last sample and differencing it from the angle of the current sample. That tells us the change in angle, right? And the way we can do that is by just taking our current sample and the complex sample, multiplying them, and then doing a tan 2 on those. On the results, which is kind of related to how Matt was doing it, although this way, instead of having to do all this complex fix-up of you do arctan of one sample and then arctan of the next, and figure out the difference, and if it's bigger than pi, you do this, if it's less than pi, you do that. It all just falls out because of the way that it hangs together, which is kind of handy. I was really worried when he started talking about this that all of my slides here were not going to be useful, but there's a small improvement, which is all that matters in academia. So this, by the way, is not quite perfect for demodulation. You wind up with some weird nonlinearities in there, and it makes kind of a mess of things. It's good enough for what we want to do. So what we're going to do is we're going to pull out that channel of data. We're going to pull out, hopefully it's worked now. Why is my keyboard not working? Oh, good. So we're going to pull out this FM signal from our samples. We're going to actually we're going to downsample it so that we don't do as much work because we don't have to. Modulate it the way we just talked about with the conjugate and ATAN 2. So that will give us our audio signal, or at least a reasonable approximation of it. From there, what we need to do is pull out this blue section. We need to pull out the RDS subcarrier. How do we do that? Again, going back to SDR basics, we're going to create a low-pass filter. We're going to take that and translate it up to our 57 kilohertz. Then we're going to apply that filter as a bandpass filter around 57 kilohertz. And then we're going to translate that back down to baseband. And then we'll decimate. We'll make it smaller again. We'll downsample again so that we're doing less work in subsequent stages. Frequency translation, since we just talked about polar coordinates, I'm going to lean on it again. If you want to change the frequency of a signal, if you want to move it up or down, what you're talking about doing is changing the rate at which it changes, which is the same as adding some phase shift to it over and over again. Does that make sense? It takes a little bit of thinking, at least it did for me. But it turns out we already know how to do that. If we just multiply a signal by a sinusoid of the frequency we want to move it to, we add that phase change. It just works. It's kind of handy. Also is very efficient on a modern CPU. And then if you want to translate down after you're done with it, you just use a negative frequency, which is, it makes sense if you do the math. The overall implementation that's, I won't say it's the easiest to read, but is probably the most instructive, is GNU Radio's Freak Exciting Fear Filter CCC Impl. This is of a frequency translating finite impulse response filter that takes in a complex number and returns complex numbers, and then implementation because C++ people are masochists. So what we're going to do here is set up a low-pass filter at 1250 hertz, translate it up to our 57 kilohertz, apply it up there, and just pull out our little blue band. Then we're going to translate it, and then we're going to low-pass it again because I use very short filters. This is an implementation detail. And then we'll decimate that down to 4 times our symbol rate. Symbol rate being the bit rate of the final output. Once we've done that, we now have just our data signal, but we don't have our data out of it yet. So we now need to demodulate binary phase shift key data. What does binary phase shift key mean? So basically what it is you take a sinusoid of your carrier frequency, or you don't move it. Or you can think of it as you shift it forwards or you shift it back, depending on the bit that you want to encode. So if you get a 1, you take and move your sinusoidal cursor up a little bit. I don't have a good explanation of this, unfortunately. Or you move it back. And that winds up changing the shape of the waveform. It is conveniently enough exactly the opposite of, well, the inverse of what our decoder does. So we can just apply our encoder, or our decoder, to this signal, and we get this. It tells us the phase if we threshold it around whether it's greater than pi or less than pi. And so we get a bunch of things that are either false or true. We also decimate, again, down to our final symbol rate. So every one of these bits is a bit in our output. This is some of the data that tell us about RDS. The gotcha here is we don't actually know which of this is 1 and which of this is 0. It's better to think of this as like red and blue or yellow and green or something like that. To know which is 1 and which is 0, we need to know the phase of the first signal, because we need to know whether it's been shifted or not shifted. And we can't know that. Happily, smarter people than us came before us, so they decided that they're going to differentially encode it. So basically, when there's a 1, we shift the phase. When there's a 0, we leave it the same. That way we know which phase is which. Because if we start decoding at the wrong point in time, they'll be flipped. But so long as they're flipped consistently, things change absolutely, right? So all we have to do now is differentially decode, and we get this signal, which looks basically the same as the last signal, unless you look closely. So yeah, so this one's got kind of a lot of short things and some long things, and this is the differential decode. And I think hopefully that makes sense. Hopefully people can see the difference between those. So far so good. Any questions at this point? Is everybody following and or giving up? Because I'm more worried about the latter than the former.
Following.
Okay, yeah, cool. Okay, so now we have our bits. We know what the RDS signal wanted to tell us in terms of 1s and 0s. RDS comes in these 26-bit blocks, right? We just have all this garbage, and we need to figure out where the actual data is. Does that make sense to people? Like, if we start in the wrong place, we're just going to get garbage. Conveniently enough, RDS, which was designed in like the 80s, if I'm not mistaken, so they built in this thing where you just put it into a shift register in the hardware implementation through a checksum, which is rather large. It's a 26-bit block. 10 bits of those are checksum. Like almost 50% of it is overhead. So you just run the checksum on each block, and then if it doesn't match, you just say, okay, whatever. You shift in the next bit, the whole shift register moves, and you continue on until it hits. Once you get a checksum that is good for any 26-bit block, you're good. That's a real data block. The probability of that not being a real data block is, so that P number there, which is 1 in 1024. So what we just need to do is scan. We just brute force walk on down this list, doing the really stupid software thing of try, nope, try again, nope, try again, nope. And whenever you find good hits, you record where they are in sample offsets. So you record what bit number you're at. The nice thing about everything being 26 bits in this system is that if you have found a good block, the next thing immediately after it should be another good block, and so on and so forth. So the offset in your bit stream, modulo 26, should always be the same. So if you started out and you nailed it, the 0 bit was the start of every block, you're going to have 0, 26, 52, and so on and so forth. If you missed it, you had like 10, like you started at the 10th bit, and you're going to have 10, 36, 62, and so on. So this is a graph that I made from some data that we extracted. I did 3 separate samples of the radio signal, showing the alignment of every candidate block. And you can see there's definite steps in there, but it's really noisy, and I'm not quite sure why that is. I suspect that it's probably due to improper filtering, because there are better ways to do filtering than what I'm doing. There's also better ways to do the sampling than what I'm doing. Like, I don't trust this RTL SDR dongle is actually sampling at the sample rate that it says it is exactly. So there's probably some drift in there, etc. But in any case, we get some good runs in terms of what offset these things are at. So notice that I very rarely said packets in any of that. I kept talking about blocks. That's because, and this is where I'm going to more or less end my discussion of RDS. RDS is packets made up of 4 blocks. Those 4 blocks come in one of 6 types, and this is the committee design shining through. The types are A, B, C, D. There's a new extension E, and there's an old extension of C prime. I don't know why C prime, but okay. And those packets, or sorry, those blocks always form a packet in the order A, B, C, D, or A, B, C prime, D, which, okay. And then the E's show up randomly and they're complicated. But at this point, once we have synchronized our bit stream and we understand where the packets are, then we're just doing protocol implementation. If you're a software person, this is not that exciting. You're just struct packing at this point. It's not super interesting. So I'm not going to belabor that point here. But I will say that at the end, for the thing that I did in this, and by the way, you should all know how much I care about this presentation because I listen to little snippets of popular music on the radio so many times in this process that this is what was in those 3 little blocks. South sit and then empty space, because that's not filled in by our state machine, / GUA space by Moby and GUA space to, so if you know what's going on here, this is Southside by Moby and Gwen Stefani on KFOG, which was one of the big hits of 1999, which the DJ informed me about repeatedly right after this play. So it was one of his top 3 albums of 1999, in fact. Anyway, so let's see if this actually worked. So we got a good sample here. And this is actually, the implementation. I'll go to the bottom. And in this notebook, by the way, you'll see a bunch of false starts. Different ways of doing, specifically, the PSK carrier extraction around how we do that low-pass filter and so on and so forth. And I'm very empirical about things. So I use filters that are stupidly small. Like I forget what it is, I think it's like 11 taps is what I'm using in here, which is really silly small, but I don't want to deal with slowness in this because it's already slow enough, as you can see. I do things a few different ways and see what actually works. So right now it's supposed to be extracting our FM channel. Then we go through decoding quadrature stuff, which has all of that stuff that I just talked about explained in comments. Here we go. Okay, cool. So here's our audio signal, which that is a different song. So sorry. So we have to wait for that to finish. Sorry. So it plays the audio for you to make sure that you've got actual good data. It shows us what the audio that we're outputting to the speakers looks like, so on and so forth. It's all here. See what we get for our final. Oh man, this is not super slow. It must be out of RAM. That's the other gotcha with this technique, is that it's very, very, very RAM inefficient. Anyway, okay, we'll let this run while I talk through the rest of this presentation. So the main points that I hope software people take away from this is that, 1, inefficient prototypes, like that awful Python notebook that I was just showing you, can give you great insights into how things work. You can learn a lot about how all of this hangs together by working through it and doing the stupid thing and seeing how it fits. Second thing is that complex number arithmetic is a really important part of doing SDR work. You should spend some time learning it. Third, FM actually demodulating it exactly is complicated. Like, there's not a closed form solution for it as far as I can tell. But if you're willing to make approximations, it just falls apart in 2 lines of code. This kind of a generalization holds across so many domains, especially in signal processing. If you can accept some noise, if you can accept some fuzziness, etc., you know, try the simple thing and see if it works. And then the other thing is there's so much cute math in this. I love it. It's just full of really cute hacks for performance reasons. So yeah, anyway, so I want to end on thanking people. First off, thanks for Ballant for organizing all of this. And as part of that, Edis for paying for pizza and beer. I want to thank Noisebridge for hosting us. There's a donations bucket over there. Seriously, throw in a few bucks on your way out because this is not a cheap space to run. And I also want to send a special thank you to Ona, excuse me, if she ever watches this. Like, thank you for getting me off my butt and actually getting back into SDR stuff like I had been to. So anyway, and finally, thank you to all of you for suffering through this and letting me know that things were going okay-ish. At that point, any questions or anything?
Show us your workbook.
So, okay, yeah, let's do that real quick. Oh, good. Okay, so there's that. Ah, good. Okay, so here is our, and actually there's another fun thing in here that I'm not going to talk about, but in here I figured out how to decay really cheaply, just kind of as an accident. If you're a math person and working through the software, you'll enjoy it. Anyway, this is me proving to myself that this thing actually works either way. And then, okay, so here we've got the offsets of all of this stuff in that 2 princes, I think it was playing. And then this is my trivial implementation of the RDS state machine. It's awful. So then we do some parsing, and we get a bunch of samples to see what's going on. Then we accumulate stuff, and yeah. So 2 princes by, who did 2 princes? Does anybody know?
Spin Doctors.
Spin Doctors, thank you. That does fit in this little gap. So, yeah, and then the rest of this is just noise. So, cool. And then,
You consider using full radio. Needed advantages of
okay, so the question, let me repeat that real quick and make sure that I got it. What's the advantage of doing this in IPython versus doing this in GNU Radio? More or less correct? So there are several advantages in doing it this way. The disadvantages to doing it this way is where I'm going to start, though. One, I don't have any code from anybody else in this. Like, I use the RTL SDR code to sample from this. This notebook also supports UHD, USERT sampling, so I use it with my B210 as well. But that's the extent of the GNU Radio that I use, is the UHD wrapper. Everything else here is Python code that is here. Excuse me. I also use a little bit of SciPy's DSP signals module, but the only things I use there are the Remez filter design thing, which I don't really need, and then their L filter implementation, which is applying a filter to a signal, which is just multiply and add and multiply and add. So I do it that way because it's much, much faster than what I'm doing. But other than that, it's all just normal IPython, NumPy, numerics. It's basically MATLAB. But that means that I don't get anybody else's code. I don't get anybody else's performance fixes, etc. in this. So it's kind of awful. I also do not get anybody's work on using the checksum to fix bits in the body. One of the nice things about having 16 bits of data and 10 bits of checksum is that you can actually correct errors with that. There's a little bit of forward error correction in there. So if you use the GNU Radio GR RDS module, it works so much better than this. Like in this little snippet of audio, it would have the whole thing filled in and, scrolling by nicely. So those are the disadvantages of it. The advantages of it are, it's all here. see. And then the other advantage, in my opinion, is that it doesn't involve GRC. GNU Radio Companion is a fantastic tool for so many things, but it is so frustrating for a software person to work with. It is just, yeah, anyway, I could go on and on about that, but I won't, because GRC is actually an incredibly powerful tool, and it's really helpful if you're somebody who understands how it works and how to hang all the pieces together the right way. But yeah, so that's kind of the difference between the two. Oh, actually, one other difference, big disadvantage of doing it this way is that you don't get any GUI. So to print it out, I'm literally just printing out an array of stuff at the end here, whereas the RDS, nice widgets to display things. So, any other questions?
What's next?
What is next? That's a good question. I'm pretty much done with this one. I brought this out of mothballs for this presentation because last month I went down to the South Bay with Tony. Thank you for the ride, Tony. I don't often make the South Bay meetings, but I went down to the South Bay and I showed Balint a picture of my antenna rotator that I'm building. He's like, oh, do you want to talk about that? I will totally talk about that next month. And then, I don't know, a week and a half ago, he pinged me asking if I was ready to talk about it. I'm like, actually, I have this RDS work that I've done that I could totally pull together and make a presentation out of, because the antenna rotator's not going so well. So I think I'm kind of done with this. It's been a really interesting process. The only thing that I want to do still is the forward error correction, because I've got the 16 bits of data, 10 bits of checksum. In theory, you can correct errors. In practice, I don't. That's part of what sucks about mine. I would kind of like to do that, but that's time is kind of precious right now. So, anyway, very good question though. Anything else? No,
Just a brief follow-up. Can you just mention what type of order error corrections used for RDS?
I actually don't remember off the top of my head. I'm sorry. I don't know that it's actually forward error correction. It might just be that it's got checksum, and so you can twiddle bits. But yeah, I don't remember. Yeah, it's the nice thing about having 16 bits is that it's pretty easy to just kind of try and see what happens. There's only 64,000 possibilities. So, was there another question over there? No? Yes.
I was just about to comment that Matt, who spoke earlier, said, wow, great hint on FMD.
Oh, excellent.
And Patch One Brown says, man, been a software person for 36 years, and I can appreciate the advantages of GRC even for a software person.
The question is, have you ever used LabVIEW?
We'll find out in a second.
Yeah, exactly. Yeah. So, yeah, I use GRC, but it, yeah, there's so many little gotchas with it. As I get better at it and I know it more in depth, it's more useful to me. So yeah. So yeah. Okay. Anything else? Cool. Thanks, everybody.
Thank you very much, Josh. All right, thank you very much for coming this evening, and thanks again to Noisebridge especially for hosting us once again. Remember, in a month we'll probably be back down in the South Bay. Keep an eye on the Meetup page and on Twitter, and let's thank our two speakers again, because I imagine Matt might still be listening on the other end. So thank you to Matt and thank you to Josh. Cheerio, see you next time.
Probably turn on some lights. That's why I didn't want you to. Yeah.
I am.
Which one is the microphone? Never tap on a microphone. It makes microphone people very grumpy. There's very sensitive little membranes in there, and when you tap on them, it's kind of a shockwave. So,
I read somewhere that there's like a key. I think it was on RDS. Is there?
RDS doesn't have a key. There's things that RDS that have a key, and that's the thing